That's good. That's good. All right, so I got screen recording on. All right, so the first thing I want to show you is something that I just did right before class today. And let me make sure that this is maximized. There we go. All right, so I want to show you this, and I can share this file with all of you later today. Just remind me, because I didn't have time, to share that file prior to the class. So this is a 6x6 adder. Okay, so that means X has 6 bits, Y has 6 bits, and then the sum, which is on the other side, also has 6 bits. So it's a 6x6 adder. But the funny thing is, it is using a 3x3 adder here. This is a 3x3 adder, or one instance of. This is another 3x3 adder, or an instance of. So the idea, because some people ask me, oh, okay, bye. I'm going to trick myself one of these days. So some people ask me, why is K0 an input pin? Why is it not always just a constant? So the answer is, this way we can stack. Okay, so this way we can daisy chain the adders. So you can use two 3-bit adders and turn it into a 6-bit adder. And then you have two 6-bit adders, and you can turn that into a 12-bit adder. So the carry output of one becomes the carry input of the next. So this way you can daisy chain, and you can chain it as long as you want. It doesn't make it go any faster, but it does make the design a little bit easier to deal with, because now you can basically increase the number of bits that you can add exponentially. Because if I just use 2 multiplier, then you can have 1, 2, 4, 8, 16, 32, 64. So it doesn't take long to end up with a design that can handle 64 bits. Is that okay? All right. So in order to understand what is a 3x3-bit adder in this case, we just look into that one. And this one does make use of the concept of a full adder. So this is one full adder, this is one full adder, and this is one full adder. So each full adder has X, Y, and also K in, carry in as inputs, and then it has sum and K out as output. Now this one does deal with 1 bit at a time. So when we look at the highlighted circuit, X is 1 bit, Y is 1 bit, and then K in is also 1 bit. And then the output, same thing. S is the sum, that's 1 single bit, and then K out is also 1 single bit. Is that okay? So this picture combined with what is a half adder, so you can see that this is a full adder. So when you look into a full adder, it looks like this, okay? So it's starting to get a little bit simpler. And when you look at a full adder, it consists of 2 half adders. So each one of these is called a half adder. This is one half adder, and this is another half adder. And then when you double click on a half adder, then you find out exactly how a half adder is done. So a half adder is nothing more than 2 bits of input, 2 input pins, 1 bit each. And we just go through the AND gate with one of them, send the output to an output pin, and then the other one we use as exclusive OR, and then also send the output to the send the output of the exclusive OR to one of the output. Is that okay so far? All right. So the way I want you to utilize this particular file, I can give it to you. Okay. Yeah. Questions? Exactly. Yep. So one thing you can do, which I'm not going to do, but I'm recording what I suggest you to do, so you can choose to do it. So the AND is doing the C. The exclusive OR is doing the R. Okay. So once you understand that part, then you zoom out to the next level, which is a full adder. So when you look at the full adder, you have X as a single bit input, Y as a single input, and then K in is a single bit input. So now you have to identify which wire is your Q. Okay, which wire is the Q, and where are the two carries coming in from in order to make the K? Okay, so you have to first remember how is K of I plus 1 defined? Okay, it's C of blah blah or C of blah blah, right? So now you have to identify where is the first C of something, which wire represents the C of something. And then it also has a second C of something, which wire is representing that second C of something. Okay, so if you go through that process and be able to label each wire in this diagram and be able to associate this diagram to X, Y, Q, K, S, and also the equations, I think that would help you understand, how everything connects in this class up to this point. Is that okay? All right, so there is a little bit of thing that you have to do. Okay, but by doing so, I hope that you will basically gain a better understanding of the material that we have talked about so far in terms of binary addition. Is that okay? All right, so just remind me to share this file. Well, okay, don't remind me, I'm doing it now. Because if I don't want to delay it, okay, and I know some of you are just want to get onto it right away, so I'm gonna do it right now. Let me put this window here, and I'll add one more announcement. Are you guys all getting the announcements by email as well? Okay, you want to set it up so that you get these by email because you don't want to have to rely on checking into Canvas every single time just to see whether there are new announcements or not. So this is a carry ripple adder. This is not a weird one. The weird one is kind of carry ripple as well, but it's not structured like this one. This one is structured differently. So this one, just I would say there are suggested activities you can do with this. That's basically what I just said earlier. And go to browse. And this one is called CR adder. CR stands for carry ripple. And then we just upload this and publish. There we go. So now all of you have a copy of this. So what we're going to do today in lab is not carry ripple adder. If anyone turns in this file as the submission for today's lab, it will get negative points. Okay, because the whole idea of a carry look ahead adder is to overcome the linear dependency that is present in a carry ripple adder. Because with a carry ripple adder, the amount of time it takes to complete the computation is proportional to the number of bits. So the more bits you want to add, the longer it's going to take. Carry look ahead is a mechanism to bypass that linear dependency by making the circuit more complicated. But nonetheless, we are basically saving time. So we are basically spending silicon, which is used to make transistors. So we are basically paying in silicon in order to get more performance out of the circuit. Is that concept okay? All right. All right. So this is, I hope it's useful. Maybe, maybe not. If you go back to the announcement, I just want to point out what I sent a little bit earlier before this one. I sent out, this thing here. This is a module that I wrote, some time ago. I was using quantum computing as the subject matter. So I will be learning something new because I cannot share with you how I learn if I just talk about, oh, this is how I learn assembly language programming, because I already know it. So in order to share with you the process of how I learn, I have to work on something that is new to me. So I'm guesstimating, how much I have to learn to really work with quantum computing is about how much you have to work to understand the material of this class. I underestimated by a long shot. It was actually a lot harder than I thought it would be, but that's even better, okay? Because I was basically forcing myself to learn something that is much more difficult than I originally anticipated. So that really made me able to examine the process and all the steps that are involved. I mean, there's nothing really groundbreaking here. So if I just go into that module, what you want to do is not to read the text and focus on just what are in the boxes, because what is in the boxes describes the steps that I took, but without referring to the technical details of quantum computing, which is not what this class is about. Is that okay? Now, when you do have spare time, like over the summer or over the winter break, and you really want to get into quantum computing, sure, read the whole thing. You can go here, go to the source, which is the ACM digital library link. And that is an introduction. It's a guide to quantum computing intended for scientists who are recently hired by the Los Alamos National Lab, getting into the quantum computing research. So it's really intended as quote unquote introductory material. But it does require a certain understanding of some math concepts and some physics concepts. I will not quiz you or anything here. Okay, so if you say I don't have time to read any of this, that's okay, not a problem. Okay, but on the other hand, if you say, well, I want to know how tech read technical, abstract, and complex material, this will give you an idea. I try to be as honest as possible when I wrote this. All right, so just extra resources that you find may or may not be helpful. It's entirely up to you to decide what you want to do. So now with all those out of the way, let me go back to Joplin also, because I wrote something in Joplin, and that's for preparing for this class. All right, so here's Joplin. All right, so I wrote down, show examples of multi-digit binary addition using carry ripple, and then use carry lookahead. So the example that I'm going to use is exactly how it's spelled out here, 0, 1, 1, 0 plus 1, 1, 0, 1. And the way I'm going to do this is to use Zernal, which is a tool where I can just write on my tablet screen, and then you guys can see my handwriting on the projector. Give me a second to get that part ready. And Zernal is an open source program. You can actually download and use it for free as well on any operating system. I find it quite useful, but that's just me. All right, so let's see, where is it? All right, so this is what I want to show in the class. And I have my own screen over here that you cannot see because this part has to run on my native screen, because otherwise this screen is not touch sensitive. It doesn't respond to the stylus, but this one does. But I'm projecting this screen, so I have to kind of make a copy of Zernal onto this screen so that you can see it. Not that you really need to know all that details. All right, so let's go ahead and carry out the math that we were talking about. And let me see, where is my browser that has the math? Nope, it was not in the browser, it was in a Joplin. So it's 0, 1, 1, 0. So we have 0, 1, 1, 0 plus 1, 1, 0. All right. So now I can show you the screen here. Okay, so we'll do it the old way first, which is the carry ripple method. So the carry ripple method is basically working on one column at a time, and the direction is from right to left, because the least significant digit, which is digit 0, is the one on the right-hand side. And then as we compute the carry bits, that will allow us to continue on the left-hand side. So that's the direction. And because this is not being stacked, this is not the second operation of another adder. So we can now say, okay, we can put a 0 here because there's no prior addition that I need to take into consideration. So now we can go through all the math. Okay, so let me label the rows first. This is X, this is Y, this is Q, this is K, and this is S. So by now, I hope all of you know where to find the definitions of all of these symbols. X and Y are inputs. There's nothing to define. Q is defined by XY. K is defined by both XY and QK using the C function. And then S is defined using the R function on Q and K. So that should be, you should know that already, okay? So we'll go ahead and carry out the computation. Q is the exclusive OR between X and Y. So 0 exclusive OR with 1 is a 1. And QK exclusive OR, the exclusive OR between QK is the sum. So that's also going to be a 1 over here. What is not explicit is how do we compute K1? So K1 is C of XY, which is the conjunction of XY. So we have 0 and 1, which is a 0. But that's only one source of K of 1. The other source is C of QK. So in this case, Q is 1, K is 0. So we have 1 and 0, which is also giving us just a 0. So in the end, we have 0 or 0, which is a 0. That is how we populate this particular 0 over here. Do we have any questions from working with column 0? Okay, so now we can work with column 1. 1 exclusive OR with 0 is a 1. 1 exclusive OR with a 0 is also a 1. But now we also want to compute K2. So K2 has two components. One component is the conjunction of XY. So 1 and 0 is a 0. And then the other one is the conjunction between Q and K. So we have 1 and 0 also, which is also a 0. The results of those two conjunctions are ORed. So we have 0 or 0 in this case, which is also a 0. So now we can put a 0 onto here. So now we work with column 2. Remember, we count from 0. So the rightmost column is column 0, and we are now working on column 2. So in this case, we have 1 exclusive OR with 1, which is a 0. And then we have 0 exclusive OR with 0, which is also 0. When we try to compute this particular carry bit, which is K3, we have to compute the conjunction of XY. But this time we have 1 and 1, which is a 1. And it is going to be ORed with QK. So Q is a 0, K is a 0. So C, or the conjunction of QK, is going to be a 0. So this time we end up with 1 or 0, which is a 1. So we put a 1 here. And then we do the same thing again. We have 0 exclusive OR with 1, which is a 1. 1 exclusive OR with 1 is a 0. And then when we try to compute K4, we look at the conjunction between these two, which is a 0. And then we say OR the conjunction between these two, which is a 1. So we end up with 0 or 1, which is a 1. And now we are all done. So do we have any questions about this particular example of binary addition? Yes, question.
So you check first the XY and then the
I look at the dependency, right? So where do I start? I basically have to use the dependency between the digits so that I can figure out where do I start and what is the next step and so on. Yep.
So you're going from like K to Q, kind of, or well, and then also the F between.
Correct. So the F cannot be computed until you have the K, right? So yeah, the K. You have the Q, the S, right? And you start from K and Q. Yep. Can you like do Q before the K? Or yes, you can compute all the Q's first. That's fine. But you cannot compute the sum, which is what we really need, until you have the case ready. And then in order for the case to be ready, you cannot start with the Q4. Q4 says I depend on K3. K3 says I depend on K2. K2 says I depend on K1. And then K1 depends on K0. So that's why we have that order that we have to figure out K1 first, and then K2, and then K3, and then K4. Once we have the case, then we can compute the sum. So we have that linear dependency here. Any questions? Any more questions about this particular example of basically working out the bits manually, but using carry ripple as a method? Yeah, you can do all the queues first. I mean, that's fine, but it won't help you because you still have that linear dependency of the case. So you're not buying anything by computing all the queues first. So you might as well compute the K when when you have the other parts ready. Well, it's easier to track, but you can always pre-compute the queues first. That's not a problem. The dependency, the problem of the dependency would be the K bits, but because the Ks have that dependency, that means the sum bits also have that dependency. So that's the problem. All right, so any other questions? Those are all very good questions. Yep.
I got lost at K2.
K2 is this bit here.
Yeah, that row. Well, you got for the X and Y, it's 1, 1.
No, because remember Ki plus 1 depends on K of I, but X of I, Y of I, and then Q of I, K of I. So what I'm trying to say is this particular K depends on these bits.
Oh, okay.
Because it's one column to the right.
Got
And that's why I define K of I plus 1 and not K of I, because the column determines the K of the K on the right on the left-hand side.
Okay.
Yeah. So that's important. Very good. Okay, so it is a very good question because once I understand the question, I can actually tell, okay, so I think you're missing the part that K of I plus 1 depends on the previous column, which is column I. So that's a very important part to understand. Very good. Any other questions? Yep.
With the machine, are they computing both K and Q at the same time?
On the machine, the queues are all computed, or they are all computed correctly already, like almost like right out the gate. So the queues are all ready. In other words, this row here, they're all ready. They're all done already. But this row here, it has some value, but they are incorrect because until all the Ks are actually determined, whatever result you get in the sum row, they may not be correct. You have to wait until all the Ks are computed first. Question?
Is Q also equal to 0, 1?
Q is, I'm not sure what you mean by that.
Like, can I put a 0 in front of the?
No, we do not, because except for K, which has K4 here, everything only has 4 bits. So whatever number of bits is in X and Y, Q and S also must have the same number of bits.
So if X and Y have like 8 bits.
And Q would have 8 bits, S would have 8 bits, K would have 9 bits. Because we need this overall carry. This is a carry out, which means for this particular 4-bit adder, do we end up with an overall carry of 1, so that if we need to carry out like an 8-bit adding, this will feed into the next 4-bit adder, so that we can daisy chain. Yeah, so the K in, which is in the form of K0, and then the K out, which is in the form of K4 here, is for daisy chaining. Because even with a 64-bit processor, which can add 64-bit, with 64-bit in one single clock, well, I mean, maybe in some occasions we need 128-bit adding, right? So how are we going to do that? Well, once again, we daisy chain. So we perform a addition of the least significant 64 bits. Whatever overall carry is the output, we feed that into the next addition as K0. So this way we can daisy chain and form, longer additions.
Yep. So in our last design, so in the first design, we had to step through every K, right, with the circuits. Right?
Well, every K depends on the previous one.
Yeah, but in the other one, we put them all together at the same time, right?
Yes,
Yeah,
it's,
but we still have to step through the daisy chain, right?
no,
No.
there's no daisy chaining whatsoever in the carry look ahead app. Yep, which is what I'm gonna illustrate next. It's hard to illustrate because when I demonstrate something, it is sequential. So I have to basically say, this is occurring at the same time as this, which is also occurring at exactly the same time as this. So let me see if I can, get that across in a demonstration. All right, so are we good so far? All right, okay. So now we're going to work on the carry look ahead adder. So I'm going to use a bar here just to separate between the two. So when we work on the carry look ahead adder, now we have to compute the G and the P terms, okay? So the P and the G's are important because we have the equations already specified in terms of K0, the G bits, and also the P bits. So at this point, if you don't remember how exactly the G and P bits are defined, it's okay, but you should know where to find it. Okay, so that is important, okay? Having read the material and be able to highlight, this is where we define P, this is where we define G, and that those terms are important for carry look ahead adding. That is what you need to do with the material that you are reading, okay? Is to basically highlight which part is important. So G is the conjunction, and then P is the disjunction of the XY bits. So in order to make the G bits, we have 0 and 1, which is a 0, 1 and 0, which is a 0, 1 and 1, which is a 1, 0 and 1, it is also a 0. So those are our G bits. The P bits are the disjunctions, which means we are ORing. So we have 0 or 1, which is a 1, 0 or 1 or 0, which is a 1, 1 or 1, which is a 1, and then 0 or 1, which is also a 1. So the P and the G bits are easily computed based on the input bits. There's no linear dependency of any kind. They only need to be going through a multi-bit, in this case, a 4-bit, an AND gate and an OR gate that has a bit width of 4. Then we can do all of those at the same time. Easy peasy, okay? So the next thing we need to do would be the qubits, okay? Because obviously we need the qubits anyway. So the qubits will also be needed. So the qubits in this case are just exclusive ORs between the X and the Y. So we have X0 exclusive OR with 1, which is a 1, 1 exclusive OR with 0, which is a 1, 1 exclusive OR with 1, which is a 0, and then 0 exclusive OR with 1, which is also a 1. All of these can happen at exactly the same time because the computation of G, P, and Q, they are independent from each other. They only depend on X and Y, and X and Y are both input pins. So that means once I have the X and the Y bits, I can concurrently compute G, P, and Q at the same time. And each one will only take one propagational delay because they only have to go through one single level of gate. Is that part okay? Does everybody understand what I just said? All right, cool. I think today I turned on the time stamping feature in Zoom. So maybe it would actually include a timestamp somewhere in the video. I don't know exactly what it's going to look like, but I enabled that feature. All right, so we got all the easy ones now, okay? And now it's time to work on the more difficult ones. So all of these is basically step 1, okay? The first propagational delay, we got the G, we got the P, we got all the Q terms. All of those are done in one single propagational delay. They're all occurring concurrently. So the next thing we need to do is we have to now figure out what is K1, K2, and K3. Yeah, I have one extra bit, so we'll see whether we can work with K4 or not, because I think that might be a good example, but it is also kind of cumbersome. So we have K1, K2, and K3. And as I said, in the previous class, I cannot remember, how those things are defined. So I'm going to have to look it up too. So I'm going to go back to my notes. Where is that? All right, so I'm going to have to look up my notes here. It is okay to need to look it up, but you need to know where to find it, okay? Which means you probably will have to read the material carefully, and you'll know where to find your stuff. All right, so we're going back to binary addition, and I know where to find my stuff. It's in section 6, and then we just have to scroll down a little bit, and now we have K1, we have K2, and then we also have K3. So we'll start with these 3, and then we might work on K4 also, okay? But we'll start with these 3. So in a very lazy way, this is what I'm gonna do. I'm just using copy and paste. And then we switch back to this one on your side, and then this one on my side. So let me see whether this is gonna work or not. Okay, try. Oh, nice. That works out. All right. So now we can work on this. And the first thing we need to work on is P0 and K0. That's the first thing we need to work on. So let me get back to my pen, which I think is already active. So we have to work on P0, K0. And that's going to be time frame 2. Okay, I'm going to use 2 here. And what is P0 and K0 in this case? K0 is 0 anyway. Sorry? It's 1 and 0, which is 0. Very good. Okay. So we can figure out this is 0. And then at the same time, we can also work on all of the other ands concurrently. So now, I'm going to do the same trick here. Go back to my own notes here, and because I cannot remember those equations, so I now look at K2. So K2 is this mess here. So once again, copy and paste over here. At some point, I'm going to run out of space, to paste it. But at this point, still in time frame 2, I can work on 2 things, because I can work on what is P1 G0, but at the same time, I can also work on what is P1 P0 K0. So we know anything that has K0 in the conjunction is going to be a 0, because K0 is a 0 in this case. So we can conclude this is a 0. And then now we have P1 G0. P1 is this bit over here, and then G0 is this bit over here. So we still end up with a 0 here. Is that okay? All of these are happening in time frame 2, or the second propagational delay. All of these conjunctions can start as soon as the P and the G bits are known. Does that make sense? So I'm going to pause a little bit here and just kind of describe a technique of analyzing a problem. One way to look at a problem is to look at the dependency. What depends on what? Because if you figure out the dependency of all the things, then you already know the order. Where do I need to start? What is the next thing that I can work on? And so on. So that's a problem-solving technique that I did not read about, but recognize when I am solving problems. Because I would look at the dependency of all the things that I need to work on. And once I figure out the dependency, I will start with the one that has no further dependency. Start with that one, and then work my way to solve all of the others. So it's just a technique. It's a mental technique to think in terms of dependency. All right. So now we can work on K3. So once again, look up what K3 is. Once again, you don't have to memorize everything, but you do want to be able to locate and figure out, okay, where did I see that in the notes? Or where did I copy that into my own notes? I think it's going to be, yes.
Why not use the A1 plus P2 and P2?
Why not use what again?
Why not use like this formula?
Because I'm trying to replicate exactly what the processor would do.
Oh,
Okay, I understand what the question is. Let me do this part, and then I'll explain why not. Okay, so let me paste this here. I think it's gonna, I think I better put it here because it's gonna overrun the other part. Okay, there we go. All right, so let me answer your question. So what your question was, why don't we use this one here in order to help figure out this thing? That would put us back in the linear dependency thing, because I need to figure out this first before I can figure out that. But now I can figure out this, this, and this in the same exact timeline as number 2. Because the idea is to maximize the number of parallel computation that I can do and reduce the interdependency of the things. But what you suggested is what a human would do, because what a human would do is to go like, okay, since we're sharing all those terms anyway, might as well do this first. And then once we know that term, we would work on this term. But then you might as well just go all the way back to carry ripple adding, because that is the simplest one. We don't even need complicated equations like this. Is that okay? But do you understand why we do not do it the way that you suggested?
Oh, yeah.
Okay.
Why do we need last part of the equation? It's always going to be 0, right?
Which one?
Last part of the equation.
The last part? Okay. So why do we always compute all of these terms? Because we want to create a circuit that works in all cases. You cannot create a circuit and go like, well, this circuit only works when K0 is a 0. But K0 may not be a 0. So I'm trying to replicate what the circuit would do, or what circuit is necessary to work on all cases. Yes.
Is K0 not a 0 because you change it?
Because you can potentially daisy chain. So I cannot assume that K0 is a 0 when I'm working on the circuit. Because the circuit has to give me the provision of what if this adder is really one step of a chain of adding. So I have to design the circuit to be more general and not make the assumption that K0 is indeed a 0. So K0 has to be a 0. Yep.
Whenever you were saying about the second delay, you were talking about just the computation of the conjunction.
Yeah. Yep.
Okay.
Yep. That is correct. And we have 3 more to go. Okay, so we have these 3 conjunctions to go. So I'm going to have to scroll a little bit. It's because it's a little bit longer. So you have to kind of scroll a little bit. And then I can write out here. P2, P1, P0, K0 is a 0. P2, P1, G0 is a 0. So all of these are just looking at what is P2. This is P2. P1. This is P1. G0 is this one here. So the conjunction is a 0. And then we have P2G1. So P2 is this one. G1 is this one here. That is a 0 as well. So we have P2G1. That is also a 0. All right. So I think we have done all the conjunctions. And these, okay, let me go back to the picture because it's better to look at the picture here. Oh, that's nice. I barely fit all of the conjunctions in one single screen. But all of these, okay, they're all occurring at exactly the same time. Okay, so in time slot 2, or in the second propagational delay, I'm doing all of these conjunctions. Is that okay? It's hard to explain because when I perform these operations, it's sequential. But when the circuit is doing it, they're all in parallel. Yes.
When you say they're all at the same time, I understand all running in parallel, but do they actually take exactly the same amount of time to complete, or just K3 slightly ever so?
Okay, so that's a very good question. The question is, do they all take exactly the same amount of time, or do they kind of like some are a little bit faster and the other ones are not as fast? As long as they're within a certain window, it's still going to be okay. So you're correct. They're not going to be exactly the same, but they just have to be within a certain window. Yep.
Is a propagational delay, is that like an actual amount of time? Or
Yes, it is. So typically it is measured in nanoseconds. Even with the current state-of-the-art transistors, it will still be measurable in nanoseconds. Because it takes time for a transistor to turn on and it takes time for it to turn off. Because each transistor that we use has what we call a capacitive load, and the circuit itself has resistance when you're trying to push the electrons from one place to another place. So combining the capacitance and also the resistance, and also there's inductance in play as well, but it's not as much. But then you have all of these constants, and CR is a constant. There's a time constant related to capacitance and resistance. For those of you who have taken electricity with calculus, you would talk about the RC constant, not CR, but RC constant. So that is what is driving the delay, is because there's a capacitive load, and the current to drive the capacitive load is going through resistance. Yep.
You keep mentioning that everything is the same time because of a clock situation.
No, this has nothing to do with clocking. We just have to make sure that everything that we are talking about here, from the first to the second to the third to the last one, we just have to make sure that all of these are happening within one clock between the transitions. Because the idea is, we know the adder is going to take time to complete its operation, but as long as it is done before we expect the answer to be available, we're still good. So we'll talk about clocking and also registers and other things that can synchronize events within the processor later. So all we need to know at this point is we just want to make sure that the entire duration of this adding is within a certain time frame. As long as it is within that time frame, we're good. Is it 75% or 50% or 60% of that time frame? We don't care. Are we good so far? All right. So next, what do? We do all the ORs. Okay. So now I know this is going to be a little bit hard because I did not leave enough space to do the ORs. So now we do all the ORs. So time frame 3 will be doing the ORs, and I will try my best to make it easier. Okay. So the OR in this case is going to be between G0 and P0, K0. And then at the same time, okay, within the third slot of time or the third propagational delay, we'll also be computing G1 or P1 and G0 or P1, P0, K0. Now remember, this is known already because in time slot number 2, we figured that out already. So this is really just this 0 here. This one here, we got to figure out already. This one, we got to figure out already. And then we have the last one, which is G2 plus P2 G1 or P2 P1 G0 plus P2 P1 P0 K0. So all of these are known already. This is this one here, this one goes here, this one goes here. So there's the arrows here do not take time. Okay, I'm merely trying to indicate that we have already computed those conjunctions already, and we are making use of the results of those conjunctions that was done in the previous propagational delay in order to perform the OR. Yes.
Are we making use of, say, like we already know, because it's conjunction, we already know that part of the second conjunction, which may be longer, we already know part of it is false or 0. So if we
cannot shortcut. There's no way to shortcut because we're trying to build a circuit that works in all cases. So we cannot make a circuit that only works, it has a shortcut because when this bit is a 0, we use this circuit. If this bit is not a 0, we use another circuit. So we have to make the general purpose circuit that works in all cases. So there's no shortcutting in this case.
I was thinking because you said it all works at the same time. For a certain circuit, is that kind of what happened? Say, when it's working all at the same time, it's just carrying over what it already calculated. Is that what we do? As the circuit continues?
There's no actual time slotting per se. What really happens is there's a delay between the time when the transistor changes as its input change to the time the output will change. So there's just that delay. Now the delay can be varying a little bit between the AND gates and the OR gates and whatnot. They're all a little bit fuzzy. So at any time there's an output. The question is the output correct? And until we complete the entire thing, the output would not be correct. So you go ahead first and then you'll be next. Yeah, go ahead.
So for us as people, it would be faster to sort of carry over values. And
Yes.
things like that, but
Yeah.
with a computer, it just is doing it all in parallel.
Yes.
And so it's easier to just access the values and do the more complicated setup, it's faster to do the more complicated setup, so
Right.
everything can just right through at once.
Exactly, because our conscious mind can only work on one thing at a time. Even though our subconscious, can actually work on a lot of things at the same time, but when you need to work on focus on something like this is conjunction, this is a disjunction, where do we get all the values and so on? It's all sequential, and that's why I said a little bit earlier, it's hard for me to demonstrate it, because when I talk about it, it is sequential. I cannot say two words at the same time. So there's no way for me to convey the parallel portion without using explicit symbols to say 1, 2, 3, everything under 2, they're all occurring at the same time, everything under 3, they're all occurring at the same time. Yeah, go ahead.
I was just going to say on that, point that, what it's doing is instead of trying to pull a value from a different gate, which will take time, it's just doing the computation again, but with an added bit.
It's not even so much again, if all the computations are continuous. In other words, the gates are taking, they're basically changing as the input changes. There's no such thing as, oh, this just got changed to 1, I have to recompute anything. In other words, the circuit is always working, it's always computing based on the input. So as soon as the input varies, even a little bit, the output would also vary a little bit. But until it is settled, we cannot say, yep, we got the answer here. Because it can be in the transition to the right answer. So the circuit is continuous. The circuit itself is continuous. It doesn't really have steps per se. But we, as we try to understand the process, we divide it into multiple stages so that it's easier to talk about. Is that okay? All right. Yeah. All right. So at this point, okay, it's in propagational delay 3, we perform all the ORs. So that means, oh, that's a 0, 0, 0, 0, 0, 0, 0. But the G's are not all zeros, right? So we have G0 being a 0, G1 being a 0, but G2 is not a 0. So now in time slot number 3 or propagational number 3, we end up with this is a 0, this is a 0, this is a 1. So all of those come to the gates at the same time. We have 3 OR gates, okay? This is 1 OR gate, this is 1 OR gate, this is 1 OR gate. They all will get their input valid at exactly the same time, and then they all generate the actual output, which is 0, 0, and 1 at the same time. So now we are simultaneously getting K1, K2, and K3 at the same time. Because what is this equation? What is this formula trying to do? That's our K1. What about this one? That's our K2. This is our K3. But at propagational delay 3, we got all of the K bits at the same time. Yes, go ahead.
We also be able to have K4 at the end of
We should have K4, just because the script is supposed to work with K4. So this is a good way to apply that gigantic and complicated thing that we were talking about. That's one way to do it. The other way is to look at how K3 looks like, and then we can try to generalize what K4 is going to look like. Is that okay? So I'm going to work on that. Okay, so I'm going to work on this generalization. Mind you that I have never done this before, so I'm going to have to say G3 looks like there's a sequence here, right? G0, G1, G2, G3 makes sense that K4 would depend on G3. And then the next thing, this one is P2, G1. So the next one, sounds like, it should only have 2 terms, but it should have P3 and then G2. Does that make sense to you? Do you guys see how I'm looking at the previous ones and then just to try to figure out the pattern of this? Because this one is P1, G0. So the index of the P is just 1 more than the index of the G, but there are only 2 terms. Same with this one. So I'm going to go, I guess this is going to be the way it's going to be. What about the next one? The next one for the previous one is P2, P1, G0. So I'm going to guess this one is going to be P3, P2, G1, right? So every index just got incremented by 1. So the next one is P3, P2, G1. And then the next one is P3, P2, P1. Okay, this one is special because everything has to, there's always one that has G0 in it. So this is the one that has G0 in it. And then there's one extra term, which is P3, P2, P1, P0, and then K0. So I'm just observing the pattern from before to basically project what this one should look like. Now, if this is what I need to compute, then all of these conjunctions really belong to time slot 2 or propagational delay 2. We know this is going to be a 0. This is going to be a 0 because G0 is a 0. This is going to be a 0 because G1 is a 0. This one, I have to look up because I cannot remember what is P3. I know G2 is a 1, but what is P3? P3 is a 1. So we have a 1 here. This one is a 1, and then so is G3 is a 0. So this one is a 1, so that means we end up with a 1 here too. Yep.
So each new row is all of the terms from the previous row, each one disjointed with the new.
Disjunction,
So like
yep.
going from K1 to K2, you have G0 plus P0 to K0.
Yep.
And then you have G1 plus P1 K1, which distributes out to
Exactly. It has to do with
P0 plus P1.
Yep.
P0.
it has to do with the distribution. So that's a very good observation. Let me kind of take the class back to the definition of the terms, because everything here is stemming from, where's my mouse cursor? There we go. So everything is stemming from this equation. Let me magnify a little bit. There you go. So everything is stemming from this one here. The K of I is getting longer and longer and longer because we figure out the details of all the previous one. So when I try to work out what is K4, K4 is going to be G3 or P3 and K3. But what is K3? Well, we know what K3 is already because we just worked it out in the previous class. So now we just have to distribute P3 over all of these terms. So those are all the additional terms. And then the G3 is the one that is sitting all the way outside. Yep. So this observation of how I worked on K4 just by observing what is K3, K2, K1 is how I end up with this one too. This is just expressing exactly the same thing, but making it a lot more concise. I describe how to generate your K of some n plus 1, just using basically this is a loop, this is a loop inside that loop, this is also a loop, and then we are just generating all of those terms by using a notation like this. Are we still doing okay so far? Are we kind of connecting the concept? All right, okay. All right, so getting back to the computation, because we are not done yet, we are close. We are not completely done, but we are really close. So getting back to here, so at the end of the third propagational delay, we end up with all the Ks already. Well, not quite, because we actually need K5 too, but it's a little bit more cumbersome. I don't want to waste too much time to do K5. K4, sorry, K4. So K4 also needs to be computed because we need one more K bit than all of the other ones. So, but I'm going to ignore that for now, okay? So with all the K bits done, the fourth propagational delay is to come up with the sum bits, because right now I got all the Qs, I got all the Ks. I just need to exclusive OR between the Q and the Ks, and I get all the sum bits. So the last propagational delay, which is 4, is looking at this is K1. So we have to start with K0. Oh, we got all the Ks already. I take it back because I forgot that the K0 is an input. All right, so we got everything. So we have all the Qs too. So these are all the Qs. So let me summarize what we have here. And Q is 1011. 1011 is Q. And the K's would be K0 is a 0. And then K1 is a 0, K2 is a 0, K3 is a 1, and K4 is a 1. So at the beginning of the fourth propagational delay, we got all of these already. We got all the Q, we got all the K's. So with one single propagational delay, because of the exclusive OR gate, we end up with all the sum bits. So one exclusive OR with 0 is 1, 1, 0, and 0. I'm not sure whether this is exactly the same. It should be the same as the other approach, which is the carry ripple approach. So let me just double check, because it'll be embarrassing if they're not the same. Yep, they are the same. But this one is only going to take 4 propagational delays. Even if you were to add more bits, more width to the adder, it will also only take 4 propagational delays. So the amount of time to compute the sum is constant. It's always 4 propagational delay. Whereas the other approach requires the K1 is computed from K0, K2 is computed from K1, K3 is computed from K2, and then K4 is computed from K3. So that one varies, okay? If you have a lot of bits, it's going to take a lot longer. This one, always just 4 propagational delay. So is that, yeah, go ahead.
So does a 64-bit adder take 4 times 16 propagational delays?
Okay, so it depends on whether we are talking about theoretical or in practice. So theoretically, if you use this approach and just extend it to compute K60 for all the 65 of all the 64 K bits, because it's ranging from K1 to K64, then it will only take 4 propagational delay. It is, yeah, because that's the whole point of carrying lookahead, is you have just removed the linear dependency between the K bits. Everybody just depends on K0. K1 depends only on K0, K2 only depends on K0, K3 only depends on K0, and so on. So that's theoretical. But when you do something like that, your K64 is going to be a very complex thing, because we have in the disjunction would have 65 inputs, and then you have 64 conjunctions. And the worst of the conjunction itself would have 63 inputs. So that's complex. You're going to use a lot of silicon to do that. And the trade-off is not worth it. So what industry does is they will make, they would use the purely carry lookahead adder to make like 8-bit or 16-bit adders. And then they would stack those, like if you make a 64-bit adder out of 4 16-bit adders, then those 4, there will be some linear dependence between those 4. But you will still end up saving a lot of time, because you're now looking at twice the amount of the propagational delay here, which is 8 propagational delay, as opposed to 64, at least. Do you see what I mean?
Yes.
Okay. So industry will only do things, they will only waste silicon when it makes sense. So when it doesn't make sense, they will go back to use a simpler circuit, because as long as you get all the computation done between the clocks, you're good. So why waste silicon to make everything be done in 5% between the in the clock period? It's not necessary to make it that fast. All right, so I think this is pretty heavy duty stuff, for continuously. So I'm gonna take roll next. Go ahead. I'll answer that question. And then
How do you compute X of the last one?
how do I compute which one?
X of the sum of the last step.
You mean this one?
Yeah.
All right, so how are the S bits defined? Or even in more general terms, how are the S digits defined in other bases? How do I compute the S digits? Well, you use an R in general, But in binary, R is done by exclusive OR. So all of that stuff is in the notes, okay? I wrote, everything is in the note. The question is, are we making the connections between all of those points? And that's why I think it is important to put all the definitions in one spot. So when you need to refer to, how is sum defined? Look it up. It's R of Q and K. But in the case of binary, R can also be done using exclusive OR, because we like to use logical operations instead of arithmetic operations, because the whole idea is to translate from arithmetic operations to binary or logical operations. So that's a good question, but it does remind you to kind of put all the definitions in one place and make connections between the concepts. Understanding is not about a single sentence. It is about how far can you reach from one concept all the way to all of the other concepts. All right. Oh, right. Tick row. I almost forgot. So let's go ahead and. This is kind of like a short break for you guys, right? Maybe. Before we get into binary subtraction. All right, so I'm going to take a look at which day. We'll use this one. We use this one. You cannot see it yet. Just give me a second to get this ready. And we'll require the access code. I'll just use delay. So make sure that you remember that delay is the access code. And I'll give you guys 15 minutes to do it. What the heck, I'll do it. I'll give you guys until 6:50 p.m. because most of you are itching to get out of the classroom by that time. So I think it's a good time to say, yeah, I think we can do it by that time. And then in the question, I'm gonna change that to I am in class today. True, false. Save the question first, and then save and publish the quiz. So you should be able to find, oh, okay, I got the wrong year. Wrong date, 2023-01, 0202. All right, so now we can search based on the date. I got the date wrong the first time. All right, so access code is right here on the screen. It is delay. Okay, we've got another 15 minutes. I think we can get started with subtraction. All right, does anyone need more time? No, we are good here. All right. So we'll go ahead and get started with subtraction. So once again, I'm going to use the same approach, which is, let's do some subtraction in base 10 first, okay? Because, we are all familiar with base 10 subtraction. Or so I would hope. All right, so base 10 subtraction, and we want to exercise the concept of, borrowing. So we'll go ahead and start with 0. Okay, I got it. So I'm going to start with 0, 2, 3 minus 0, 2, 6. Okay, there we go. All right. So once again, we have the x, the y. This time the q is the single digit difference. Okay, so it's not the single digit sum, it's the single digit difference. And instead of having k, I have t. Basically, that's the same thing as the borrow, but I'm not going to use B because B is going to define the function. And then we have D here as the difference. Okay. So the first thing is, what is 3 minus 6? All of you are going to say -3, which is correct, okay? But if you try to explain -3 to an elementary school student, it's like, what is a negative number? It doesn't make sense. So to a elementary school student, 3 minus 6 is going to be, I mean, the first thing that they were taught that 3 is less than 6. You cannot take 6 away from 3. So what do we need to do? We need to borrow. Okay, so you need to borrow a 1, which is in this case a 10, a quantity of 10 from the digit on its left-hand side. So the 3 becomes a 13. 13 minus 6 is 7. Is that okay? So the single digit difference between 3 and 6 is 7. But we end up with a borrow from the next row, from the next column. T0 is just like K0, unless we are chaining, it's assumed to be 0. So now we have 7 minus 0. 7 minus 0, we also want to only focus on the single digit difference. So 7 minus 0 is just 7 in this case. So does everybody understand the concept of a single digit difference, which is analogous to a single digit sum? It's basically how you explain subtraction to a person in elementary school, like maybe second or third grade. Is that okay? All right.
I don't know where you got the 13. You said it was 13, the 3 and the 6. And then
Okay.
you got the 7.
So, okay, let's pretend we are not in this class. So let's pretend that you are trying to teach an elementary school student of how to perform subtraction, but multi-digit. Is that okay? Okay. So so we have a 3 minus a 6. The elementary school student said, there's no way you can take away 6 from 3 because 3 is less than 6. So what you say is, well, you're correct. We cannot, subtract 6 from 3. Let's go ahead and borrow 10 from the digit on the left-hand side. So now it becomes 13. Can we subtract 6 from 13? The answer is yes. And 13 minus 6 is 7. Is that okay?
Yeah.
All right. So now we have 2 minus 2, which is really just 0. 0 minus 1, same concept, right? You cannot take 1 away from 0 if you don't understand negative values. But what you can do is to say, well, I don't have enough money, but I'm going to borrow. So you're going to borrow from column 2. Because remember, this is column 1, this is column 0, so we're going to borrow from column 2. So, but you better make sure, because somebody has to keep tab of all the borrowing. So now we say, yeah, we are borrowing. That 1 becomes a 10. Okay, so it becomes 10 minus 1, which is a 9. Is that okay? All right, so now we have the last column, which is column 2. 0 minus 0 has a single digit difference of 0. 0 minus 1, man, it's kind of the same thing. You cannot subtract 1 from 0 if you don't understand negative numbers. So we're going to have to borrow from column 3. So now we have 9 here, and we're done. So you guys are going to ask, how can this happen? You had $23 in your pocket. You're supposed to spend $26. And we end up with $997 in the pocket. I want to be in that business too. So there's a reason why there's a borrow just hanging over here. Because that is the bank telling me that I owe the bank $1,000. So I have $997 in my pocket, but I owe the bank $1,000. So when you look at my net worth, it is not $990 something. It is -$3. I owe the bank $1,000, even though I have $997 in the pocket. So my net worth is negative. Yes.
You took out, sorry, it's
took out $1,000 loan to pay the months.
You just need to open a different credit card, right? Daisy chain credit card. That's what some people do. It's like, I owe this credit card money. So we'll just daisy chain. The borrow from here becomes KB at T0 over here. Use this up. The overall borrow becomes the borrow of the next one, and so on. All right, so I'll be good here with this representation of subtraction. So if I were to ask you, how do you write the B function? So we'll just say that your QI is B of XI, YI, which is the single digit difference between, when we perform XI minus YI. How would you define that function? So B of, I'm just going to use XY here as the variable or the parameter. How do you write this function? How do you write this expression here? There are a few ways to do it. Yep, go ahead.
Xi minus mod 10.
Okay, so now it depends on whether mod can return negative values or positive values. So if
Well,
I'm
mod
going
would
to,
always be returning a positive value.
does it?
Passing it, doesn't it?
I do not know.
If you take -3 mod 10, I feel like that would give you 7. I don't know.
I do not know. So we can always make sure the numerator is non-negative to begin with, right? So in this case, if I want to make sure, I can say 10 plus X, the whole thing minus Y, and then this entire thing mod 10. Would that work? Because the worst case is X is already greater than or equal to Y. It's not a problem because I'm going to mod 10 after the entire thing. Is that okay? Well, let's plug it in and see when it works, right? So 3 and 6, okay? X is 3, Y is 6. 10 plus 3 is 13, 13 minus 6 is 7, 7 mod 10 is 7. Yep.
I checked it on Google, looks like mod function just always return positive.
Oh, it does.
So I think you might just get with the mod.
Okay, so without the 10 plus, even better. Okay, very good, thank you. But this works too, okay, just in case the mod operator that I'm going to return you a negative value here. Yep. All right, well, as I was saying, just in case the mod operator returns a negative value, this always works, okay? But do we have any idea, do we have any questions about the concept of how to compute the, oh, you know what, I just messed up, totally messed up. Because this is not supposed to be B, this is supposed to be R. Excuse me, this is supposed to be R and not B, B for borrow. I now remember what R is supposed to be. R is supposed to be result. Yep. Yep, that should be R as well. Yep, there you go. Yep.
Could you, instead of adding 10 to make sure it returns positive value, just do absolute value?
No, absolute value is not the same thing. Cannot use absolute value here. All right, so what, yeah, go ahead.
I can't really read what you wrote down there. Is it 10 plus X?
You mean this thing here?
Yeah, sorry.
Okay, let me rewrite it because I accidentally clicked one of the buttons on the stylus, so it kind of just messed up. So let me redo it one more time. So it's 10 plus X, the whole thing minus Y, and then this entire thing mod 10. All right. So what about the borrow thing? What about this thing here and this thing over here and this thing over here? How do we do that? So the borrow, when we subtract X, when we subtract Y from X, do we need to borrow? Is a question of whether Y is greater than X. So that means the easiest way to define this is to say X is less than Y, question mark 1, colon 0. That's all we need. Does that make sense? If we are trying to subtract more, which is Y, from X, then we need to borrow.
T, right?
That will, well, not exactly. T can get a borrow when we subtract y from x, but it can also get a borrow from t subtracted from q. So the relationship between t and the b function is analogous to k, the relationship between k and the c function. So let me go ahead and finish that, okay? So we'll go ahead and say q of I is the redefined R, okay? And there's a reason why I continue to use R here, okay? Because in general, in other bases, R is defined differently compared to the one for addition. But for binary, guess what? They're the same. And then D of I is going to be the R of QI, KI. And then T of I plus 1, this is a big clue. It's like, oh, we have seen this before. Last time, we were talking about K of I plus 1. So this one is very much analogous. It is the B of XI, YI, or plus, okay? I don't think we have enough time today to talk about why only up to one of these two can be 1. But I think, some of you can probably work this out. This is T of I. There we go. So when you look at the structure, not so much the letters or the variables or the functions, but when you look at the structure of how T of I plus 1 is defined, and you compare that to how K of I plus 1 is defined, you go like, looks similar with a few minor differences, right? So instead of K, we have T, instead of C, we have B, but other than that, looks awfully similar. So at this point, okay, everything on this slide here is specific to base 10, right? Now, how do we know? Because R is specific to base 10. So the question is, if I want to learn how to do subtraction, multi-digit subtraction in base 7, what do I need to do? Change the 10 to a 7, right? So if I push this one more and say, I want to convert everything to work with base 2 numbers, binary numbers, what do I need to do? Change the 10 to a 2, right? But then we encounter the same problem as last time, because we don't want to deal with arithmetic operations, plus arithmetic, mod, even worse, comparison is kind of arithmetic operation too. So we don't like those operations, even though this will work with base 2 just fine. So in the next class, which is on Tuesday next week, we'll go ahead and take a look at the special case of implementing R and B when we are focusing on just base 2. Can we use Boolean operators instead of arithmetic operators? The answer is yes. Okay, and if you read the notes ahead of time, you will also know how we need to make those changes. So we do have a long weekend. Please read the module on binary subtraction. Okay, as you read, you might need to take notes. Okay, if not, you can. Okay, I can only say that everybody takes notes differently because your brain doesn't function the same way as mine. So the way you take notes will work only for you. Okay, but I'll be available to answer questions. Oh wait, wait. Just one more thing, because I need to give you the access code and release the lab for tonight. So give me one more second before you head out to the lab. See, I know you guys are very excited to get started with the lab. But I still need to give you the access code so that you can get started right away. So it is carry lookahead adder part 1. There are 2 parts to it. This part here will be just like a quiz. This is a file submission, just like the first 2 assignments or the first 2 labs. There's also a test driver included too. So you might want to make use of the test driver. So with this one, I set up everything already. So I think, oh, but you need to know the time. Never mind. I need to get in anyway. So give me a second. I thought I could just unlock it. I mean, just let you see it. So the access code is 3x3 lowercase part 1. Just write it down, take a picture. Oh, or ask the person next to you in the lab.
Sorry, I ask just a question. So why don't these teachers, like in particular, but general teachers, don't allow us to do like
Report?
no do advanced work. Like for instance, you publish the lab just before,
Mhm.
and I presume the homework will be similar. Like you get to here to there.
Oh, I can answer that question.